In classrooms and labs all over the world, people depend on calculators to do all sorts of math. But have you ever wondered how a calculator works? Fundamentally speaking, calculators are just a special type of computer, and like all computers, the only math they're really good at is arithmetic. So the question of how to make a functioning calculator is to present all the math you want a calculator to do in terms of arithmetic. Polynomial functions can be calculated using only arithmetic, but what about all the other functions, like trig functions and exponential functions? If only we could make those functions more like polynomial functions. As it turns out, that's completely possible, thanks to the power of calculus. One of the most powerful concepts in calculus is that of the derivative, which is basically the instantaneous rate of change of a function. Now, what does that mean? Well, it's essentially like taking a specific point on a function and being able to tell exactly the rate at which the function is changing at that point. Because the derivative maps the rate of change of functions at specific points, the derivative itself is subject to change as you move across the function. As it turns out, it's possible to actually calculate the derivative of a derivative in what is called a second derivative. Essentially, you're determining the rate of change at which the rate of change is changing. Ooh. It's even possible to take a third derivative or a fourth derivative or however many derivatives you want. Each derivative you take will tell you something about how the function behaves and will allow you to make predictions about where function values will go in the future. Since derivatives describe how a function behaves, what if we were able to construct a polynomial function that shares the similar derivatives to a different function, so that the polynomial function will behave in the same way? Humans have found ways to do exactly that, using things known as Taylor polynomials. A Taylor polynomial is a polynomial function that mimics the behavior of a non-polynomial function. They are constructed by looking at a specific point known as the center on the non-polynomial function, and constructing a polynomial that shares the same first and second and however many derivatives you want to take of the original function, and therefore it takes on the same behavior as the non-polynomial function because it shares similar derivatives. Because Taylor polynomials mimic the behavior of non-polynomial functions, calculators often use Taylor polynomials to calculate values of non-polynomial functions because they can be solved using only arithmetic. And they can be constructed to have values that are extremely close to the actual non-polynomial function's value. To demonstrate the power of Taylor polynomials in action, I use them to create my own calculator, here in this computer program, Taylor.c. Let's run my program to calculate the value of the cosine of 2. So here I'll input 2 into my cosine function, and voila! My computer has spat out this large polynomial function it generated to approximate the value of the cosine function. And down here has shown this value it calculated using this polynomial. Notice how this value is within 1/100,000th of the value shown here by this calculator.